Okay, is the slide up now? All right.
Yes, sir.
Okay, great. Yeah. So continuing our discussions on oxidation. So we figured out that uh, extractive metallurgical processes, for example, uh, formation of metals from the oxide or sulfide ores, would require that you uh, keep your oxygen partial pressure in terms of oxide reduction less than the PO2 equilibrium. At a particular temperature, there is a specific oxygen partial pressure, which is the uh, neutral point, above which the oxidation would be favored, in the sense that del G for the reaction becomes negative, and below that oxygen partial pressure, the metal formation will be favored. So the objective of a reduction process from ores is to keep the oxygen partial pressure always slightly lower than the equilibrium, so that the process can be continuous and you will continually form the metal, right? And likewise, you can have simple diagrams for the carbonates or sulfides and chlorides and then things like that. Okay. Now, taking our discussion forward, there was a method or an approach to standardize everything, right? And it was way back in 1944, Ellingham, he experimentally plotted the del G values with temperature for so many different materials. For example, aluminum, silicon, platinum, nickel, copper, cobalt, all sorts of metals and their respective oxides, right? And that means the reaction is for the oxidation of metal reacting with oxygen, forming an oxide, right? And the interesting thing that he figured out, that this del G versus temperature, the relationship was linear. You can plot it on a kind of linear scale, uh, despite the terms t to the 2 and t to the minus 1. You see that in many of the standard free energy terms, you'll see a of temperature are really low, and such that it doesn't really affect the nature of the curve or the relationship that we are getting, right? So you could write the del G versus T relationship in the form of del G is A plus BT, which is, of the form Y is mx plus C. So this is, or if you plot del G 0, that's the standard Gibbs energy on the y-axis, and temperature on the x-axis, you'd get these two numbers. And if you compare this thing with our standard formula for del G, that is del G 0 is equal to del H minus T del S. Right, so there's one term which is the temperature independent term, and the other one which is the temperature dependent term. So you see that this A is almost equivalent to the enthalpy part, this del H part here, right? Del H minus T del S. That means this B is representative of the negative of del S0. Right, so this is kind of coming out to be a simple formula, which perhaps can be useful. Right, now if you look at the typical Ellingham diagram for this is not really called the Ellingham diagram. Ellingham diagram is called when all the metals, or most of the metals, are plotted on the same graph. Okay. This is, of course, the oxidation diagram for silver oxidation. No, and this is the del G curve. This is the del G curve, and this is for with temperature. All right, and it's almost close to what experimental values are, although I have drawn it separately. These are not by taking some points, but then just plotting the relationship on the graph. right? This could be slightly changed, but then it's largely almost true to the values. And if you look at this, some of the features, if you look at this is a straight line, and this is del h minus t del s kind of straight line, and you'd see that del h should be what do you call y is mx plus c plus c something which kind of hits the zero, right? So this turns out to be the intercept, and this is the del h part, right? And this is del h part not here, but we have plotted the x here, right? This is the x, and this x can go back to almost, if it's 300 and 500, then 300 to 6 is almost about here, would be 0, and at this point down below where this curve would hit, that would be the del h value. That would be the del h value. All right. And what about the slope? This, you see that this oxidation curve for silver has a positive slope. This is slanting onto the right. So this has got a positive slope. All right. And that would be the negative of delta S0. Because if you look at here, this is this B. This B is entropy change in entropy with the negative, because this is del H minus T del S. So this B has to be minus del S0. So that means the slope is actually negative of the entropy change in the process, right? And we'll see what's the entropy change in the process, right? Now, oh, okay, let's see what's the, let me go to this one. Okay, the entropy change during oxidation. Let's discuss this one first. Right now, if you a generic expression for the oxidation of a metal, and this one would be for a divalent metal, and this A plus O2 is AO2. Instead of divalent metal, if you take a monovalent, then you can write uh, is it a divalent metal? No, it's not a divalent metal, right? This is like a titania kind of thing, or titanium, or sort of zirconium, or things like that. Okay, if you take a divalent metal, it'll be 2A plus O2 is 2AO kind of thing. And likewise, if you take a covalent metal, Na2 thing. So with regards to 1 mole of oxygen, you can simply write that. And that's not going to change too much of things with regards to entropy, at least. Okay. So this is a mistake. This has to be a quadrivalent for an equation like this, but it doesn't matter. Talk about a generic expression where A reacts with O, gives some form of an oxide, which is AOX. All right. Now, if you look at the change in entropy in this whole process, right, and right to calculate the standard change in entropy, you see that entropy of this one, this is the product, minus the entropy of the reactants, that's minus SO2 minus SA, right? And that will be the combined, the total entropy change. But if you look at this, what is the entropy of AO2, and what's the entropy of A vis-a-vis what's the entropy of oxygen? All right, you know that this A is a solid, oxygen is a gas, and AO2 is a solid. That means what happens is a solid is reacting with a gas and forming another solid, and there is no gas left because the gas actually gets into the solid and forms a bigger solid, a bigger molecular formula. But then the gas is not there anymore. Now, with regards to entropy, what could be happening? A solid, as it's an ordered solid or amorphous solid, but it's a solid, it's a condensed phase. So comparatively, the entropy, the absolute entropy of oxygen, a mole of gas, is much, much higher than that of a solid. much higher than that of solid. All right. Likewise, AO2 also is much lower than oxygen. The oxygen entropy is much higher than that of the AO2 solid. In a way, you could say that the entropy of A and AO2 can be comparable. Okay, but the entropy of oxygen is much higher because the fact that this is in a gaseous phase. All right. So when you try to write down the total change in entropy, that comes out to the point that S0AO2 and S0A are insignificant quantities, so small that they actually don't make an impact on this number. So you can safely neglect this. Right. And here also you would see that even if it is some positive entropy and this is some positive entropy, you are actually getting this minus this. So anyway, these are anyway insignificant numbers. At the same time, this one minus this one actually is nothing left. All right, so we don't actually have to get into the details of what exactly the absolute entropies of these solid compounds are. So eventually, this del S0 becomes minus SO2 0. All right, that means the entropy change is only because of the disappearance of 1 mole of oxygen. So this is the mathematical formula. But then if you look at physically what's happening, which is what I had told you in the beginning, that a metal reacts with a gaseous material and forms a metal. All right. In the process, what is happening is that a solid reacts with the gas and then forms a solid, and there is no gas left in the products. That means in this whole process, this much of gas has been consumed. With regards to the gaseous or the phases, this much of phase is completely lost. This much of gas is completely lost. That means this much of entropy is also lost or contained in the system. So in this whole process, since S0 is a bigger positive number, del S0 is a negative value. It means the whole system goes for negative entropy. Entropy at the end of the process is much lower than it was in the beginning of the process. Whereas if the entropy change is negative, what is the negative of negative? Is positive. All right. That's one of the reasons that when you talk about this graph and then you talk about the slope of the graph, it is always a positive slope because the process itself is towards a metals is going to form an oxide, which is always going to be leading towards a reduction in entropy. And that's the reason these curves, okay, all of it would be almost parallel to each other. Okay, and that's what is Ellingham diagram. Of course, I should have put a diagram as such. I'll show it in the next class. So any metal that you take and their oxidation, you try to plot the del G versus T, they are all going to line up parallel to each other because all of those things lead to this disappearance of oxygen and form another oxide phase, which is a solid phase, right? And the entropy change, when you normalize it with the reaction of 1 mole of oxygen, all of these are going to be almost parallel to each other with subtle variations, of course, but then by and large they're all parallel to each other. That's what is called Ellingham diagram. But in the same one diagram, the bigger scales, you'll have all those oxidation diagrams plotted together only on one plot itself, right? Okay, now, so this is what we've considered already in the reaction of silver, or for that matter, any other reaction. The length of the intercept of the silver oxidation of line T0K is a standard change in enthalpy. Right? So talk about line 0K means this is an x-axis goes this way, and this is where you get 0, and this curve continues. It's downward thing. Then at the y-axis, it meets at some point, which is going to be perhaps about minus 60 or something, and that's minus 60 kilojoules is going to be the distance from 0 to this much, and that's going to be the intercept, and that intercept is nothing but your standard change in enthalpy. That's going to be your standard change in enthalpy, right? And del S0 is the negative slope of the line. Note that the reaction involves the disappearance of 1 mole of gas, therefore entropy decreases during the process, which is what just we discussed, right? And one interesting thing is that del G0 at T is 462 Kelvin. So you talk about this one, and this is the line where the del G0 line, it sort of intersects. That means this is the equilibrium line for which at 462 Kelvin, at 1 atmosphere, the silver and oxygen and silver oxide are all in equilibrium. They coexist. All of these coexist at this point at 1 atmosphere. All right. And if you, in this 1 atmosphere is the partial pressure of oxygen. If you write an equation of del G's RTL and PO2, and PO2 is 1 atmosphere, that makes this ln PO2 is 0, and that's why del G is 0 here. Right? Okay. So yeah, that's what it is. Del G is RTL and KP. This is RTL and PO2, which implies that PO2 is 1 atmosphere. All right. This is minus RTL and KP. And okay, now what would happen if you change the temperature in the silver oxidation? We're taking silver oxidation just a case in point. You can extend this argument or discussions to any other metals or any other temperatures that you like. All right. So taking this curve, let's consider what would happen for a situation with temperature T1 and temperature T2, and how these temperatures are different is that for the equilibrium temperature at 1 atmosphere, which is 462, T1 is much lower than that, and T2 is much higher than that. And that perhaps would give you contrasting features of equilibrium, and that's what we're going to see. What it says is at T1, okay, del G becomes more negative. If you look at this T1, so we're looking at this region, okay. Now if you're looking at this region, del G is plotted here, and then if you talk about this curve, this is a curve of interest, and you see negative value. Oxide phase. Much more of the oxide phase would be formed. So that's because del G is so negative, it'll lead to a spontaneous oxidation of this metal. That means if the temperature is lower than the equilibrium temperature for that, equilibrium temperature for that particular pressure, then a spontaneous oxidation of the metal would happen, and then this is going to be much higher, right? So yeah, this is the same thing. Now, if you look at this for this temperature, let's say, if at this temperature the spontaneous reaction of metal happens and it forms oxide, then would there be a change in the equilibrium partial pressure of oxygen for oxidation of silver at this temperature? That's my question. See, I would like you to understand this one. So, for example, at a temperature 462, what is the partial pressure of equilibrium partial pressure of oxygen for the oxidation of silver? That is 1 atmosphere. That means the temperature, the oxygen partial pressure more than 1 atmosphere, spontaneous oxidation will take place. Less than that, there'll be reduction. So here the equilibrium partial pressure of oxygen at 462 is 1 atmosphere. What is going to happen to the equilibrium partial pressure of oxygen at T1? Because you know that this already is a much more negative del G. That would mean that the equilibrium partial pressure of oxygen for the oxidation of silver at T1 is going to be much less than what it was at 462. That means at 462, the partial pressure of the equilibrium partial pressure of oxidation uh, is 1 atmosphere. So the same quantity at T1 is going to be much less than 1 atmosphere. All right. That means this is much more favorable condition. That means this guy at this point is ready to, going back to our earlier example, this guy is going to watch a movie even at 300 rupees, whereas this guy, this condition, where it demands 600 rupees to go and watch a movie, he can do it in a much lesser price. Okay. Now take this argument to the next temperature, which is T2, which is much higher than 462 Kelvin. Turns out the things are going to be slightly, completely reversed. That means when we talk about T2 and then at this temperature slice, if you look at the nature of this curve, this corresponds to a positive del G value. Okay, and positive del G value, you see that it will be a backward reaction. I mean, the positive del G value tells you that the del G value is negative for the backward reaction. That means the backward reaction would happen, which you'd see that the oxide phase would get reduced to the metallic phase. All right, and that's only because of this, there's a positive number. And if we consider that what will be the equilibrium partial pressure of oxidation at this temperature, turns out this is going to be much higher than what it was at 462 Kelvin, which is at 1 atmosphere. So here the equilibrium partial pressure of oxygen at T2 would be, oh man, there's a mistake. These are not going to be T2 numbers. I'm sorry. So here we are talking about PO2, equilibrium at T2 is going to be more than 1 atmosphere. And going back to our earlier example, we could say that this is that he's ready not at 600 rupees to go to the movie. He'll demand probably 800 rupees. Then only he'll go to watch the movie. 300 rupees to watch the movie. This guy is okay with 600 rupees to watch the movie. This guy demands 800 rupees. Anything less than that, I'm not going to go to the movies. So any pressure less than like 1 plus delta, I'm not going to get oxidized. Any pressure less than 1 atmosphere, I'm not going to get oxidized. Any pressure less than 1 minus delta, I'm not going to get oxidized. So just about 1 minus delta, it gets oxidized. Just about at 1 atmosphere, it gets oxidized. Just about 1 plus delta atmosphere is when it gets oxidized. And when I say delta, that's the additional pressure that is required when you come from this T to T1. I'm sorry, T to T2. That additional pressure on top of 1 atmosphere is required, and T to T1, the pressure less that is required than the one atmosphere. All right. So if you go higher, then the requirement of the limiting pressure, this PO2 equilibrium at this temperature, keep on increasing for the same oxidation curve when you go to higher temperature. Right? Okay. So this we kind of discussed. Okay. Now we talked about this curve, and we know that the delta change in entropy for all of these oxidation of all of these metals are going to be almost parallel to each other. But then, so it makes sense to see how are these curves, meaning del G. So you see the same sort of valency. We're considering, of course, manganese and cobalt both can have variable valencies, but here we're considering the divalent ones, the simplest forms of their oxides. All right. So, and you can write the del G equations for each of these curves like this. For del G manganese, it is minus 769 kilojoules plus 145.6 T. This J is for joules. And for cobalt oxidation, and del G is minus 467.8 kilojoules plus 143.7 T joules. Right. So you see that some similarity here is that here one oxygen is reacting, 1 mole of oxygen, and 2 moles of the solid, a metal solid, form 2 moles of the oxide, and here also 2 moles of the metal solid form 2 moles of the oxides. Right? And if you look at these numbers, look at this. This is, you can write this del G is del H minus T delta S. Right? From this equation, you can see that del S is what? It's minus 145.6. Right? And look at the del S here, minus 143.7. That will be the del S for this reaction, for the cobalt oxidation reaction. You see that these two reactions are kind of close. They're not much different. All right. So if that were to be true, then how do you expect the curves to be? They're almost going to be parallel to each other. But of course, the difference is this. Now this is the intercept, and this is the intercept, and this is what? This is del H. The enthalpy changes are much different. That means the intercept of each of these lines are going to be much wider apart. And let's see how does it look. This is what it is. All right. So this is the del G line for cobalt oxidation. This is the del G line. Look at this one, the slant line. And this is the del G line for manganese oxidation. All right. And if you I think we are on the same scales. Okay. So we are on the same scales. That means if you impose this graph on this, it'll appear that del G is here, and the del G is here for the cobalt oxidation, and this del G here for manganese oxidation would actually be somewhere like this. So you see that these two curves are going to be parallel to each other, but then they're displaced by some quantity. And how are they? You can see it very clearly. That this del G curve is composed of this del H term and this minus T del S term. Right? Now minus T del S term is, you know that del S for each of these numbers you can find out is minus 145.6 here, minus 143.7 here, kind of really similar. That means that fixes the slope. Okay, and now this term, the whole term of minus T del S would actually stem from zero, from absolute zero, and the whole value of it is zero. As temperature increases, okay, you multiply the temperature with a constant quantity, that is minus 145.7, minus 145.6 for one, and minus 143.7 for one. Right? So this the negative quantity is being multiplied with temperature as we go up here, go up in temperature, yielding a straight line like this. This is the whole term for minus T del S. Okay. And what was this del H term? So in the del G curve, this is zero, this is a flat line, it's zero. And del G is minus 769,400 for the manganese, or for the cobalt is minus 467,800. So this is cobalt, we're plotting minus 467,800, minus 468 kind of thing. And that is kind of constant, and it doesn't depend on temperature too much. Or here, it doesn't depend on temperature at all. Or in practice, it might depend on slightly on T, so we have neglected that. So from this curve, you'll see that it's a straight line. It's simply straight line. It doesn't cut this axis, right? It's simply displaced from zero by minus 467, minus 467.8 kilojoules, and it's a flat line like this. All right. So when you want to get the del G curve, you'll have to add this curve and this curve, which is giving you this curve. Right? And a similar exercise you can do, and you'll find this T del S curve for both of the terms here are kind of similar. But then when you try to plot the del H curve, you would see that it's also like that, like the cobalt oxidation. But then the manganese oxidation is slightly shifted from here and it shifted by the quantity from 0 to about what? Minus 769.4 kilojoules. Minus 769.4 kilo. This is the del H line for manganese oxidation. And when you add up this one and this one, you get a curve like this, which is the oxidation curve for manganese. All right. So here the point you want to take is that the more negative the value of the del H is in a when you try to compare the oxidation of two metals, then it's the more negative the value of the del H. That's where it's going to be more stable, much more stable oxide. Okay. Because correspondingly, you'll see that the oxygen partial pressure required for any temperature, the oxygen partial pressure required to oxidize this one is going to be much higher than what it's going to be for this one. Because this one, the delta H is so negative. So we plot this one here. Here is the del H value for cobalt oxidation. Here is going to be the del H value for manganese oxidation. Okay. So manganese likes oxygen too much. Right. So it only requires a little bit of oxygen to become an oxide as compared to cobalt. That means manganese oxide is much more stable than cobalt oxide. So accordingly, the partial pressure of oxygen, equilibrium partial pressure of oxygen at any temperature for manganese is going to be much lower than the equilibrium partial pressure of oxygen for the oxidation of cobalt at any temperature, the same temperature. So fix the temperature and try to compare what is the equilibrium partial pressure of oxygen for the oxidation of cobalt and the same for oxidation of manganese. You'll see that the PO2 required to make this one oxide, to make cobalt an oxide, is going to be much higher than the PO2 required to make manganese an oxide. I hope you'll have to carefully think about it, and it's very simple and straightforward. Just that we are talking a little faster. That's why you might not be able to sort of get a hang on that. It's fairly simple, right? And if you like to see the sort of dependence of this is exactly what we've been talking, and you see that this logarithm of the rate constant here can be written in the form of minus del H by RT term and plus del S by R term, and which is equal to ln PO2 to the minus 1, which is 1 by PO2. Right, and this you can write the partial pressure of oxygen for equilibrium at a specific temperature in the form of exponential forms of del H by RT and minus del S by R, and you know that. So so you'd see that this del H is kind of constant here, or constant meaning the nature of del H is fixed here. Okay, it's always going to be an exothermic reaction, because we're talking about oxidation of metals, right? So you talk about any metal when you're talking about cleaner oxidation, then del H is always going to be negative, right? So this PO2 equilibrium at specific temperature would increase exponentially with temperature, right? That means what does it mean? It means for the PO2 required to make a metal oxidized uh, would actually increase with temperature. This is what we talked about here also, right? So this temperature vis-a-vis this temperature, or you can talk about this temperature as well, right? So for each of these temperatures, there is a specific amount of oxygen required for this metal to make it oxidized. All right. Now we are not talking about any different types of oxides or different types of metals. We are talking about a specific metal and its oxide. Okay, its transition from the metal to the oxide phase. Now, for every temperature, there is a specific partial pressure in the metal. And the temperature increases, this also would increase. All right. And again, for at any temperature T, talk about constant fixed temperature now, and compare the oxidation of two different metals, for example, cobalt and manganese. Right. So in that case, we're talking about, let's say, 500 Kelvin. We're talking about 500 Kelvin, and we're comparing the partial pressure of oxygen required for the oxidation of cobalt versus the oxygen required for the oxidation of manganese. And you see that the PO2 required decreases as del H becomes more negative, which is exactly what I was discussing with you moments ago. That for this one, and for this one, if you for a specific temperature, okay, for a specific temperature, manganese, since its oxide is more stable, that means del H is much more negative value, then for a specific temperature, the amount of oxygen required for it to become oxidized is much less than the amount of oxygen required for cobalt to be oxidized. That's why it says, and that's why is that? Because del H is more negative in the case of manganese here. All right, which is what it says, that at any temperature, the PO2 decreases and del H becomes more negative. For materials where the del H for the oxidation is much more negative, the PO2 equilibrium required for that metal to become oxidized is much lower than some metal with the del H which is less negative. All del H's are going to be negative. You know that for the oxidation reaction, talk about any metal, all del H are going to be negative. But then someone is more negative, someone is less negative, which is example what is given here, that cobalt is negative but less negative as compared to the manganese oxidation enthalpy. So in that case, the partial pressure of equilibrium at a specific temperature for the oxidation of manganese is going to be much lower than the PO2 equilibrium temperature required for the oxidation of cobalt. All right. So this is simply what I said. The equilibrium partial pressure of an oxidation reaction increases with temperature, which is a statement for this term, for the first one. The equilibrium partial pressure of an oxidation reaction increases with temperature. Simply, this is a mathematical form, sort of, and this is a simple statement. All right, and this one is a simple statement for the second point. It decreases as the standard enthalpy change becomes more negative. The standard enthalpy change, if it is more negative, the oxygen partial pressure, equilibrium oxygen partial pressure required for the oxidation, which is increases. I'm sorry, it decreases. All right. So I think it gives you a fairly good idea about the thermodynamics of oxidation, and maybe in another class we'll talk about comparable oxidation, and we'll see how all of those graphs put together, how does it look like? Point one, and point two, what happens when during an oxidation, if either the metal or the metal oxide change their phase to become either a liquid or solid to liquid in the case of metal, or solid to liquid in the case of a metal oxide. All right, and how would that affect the shape of something like this. Right, that's what we talk about. And one more aspect I will talk in the next class is what would happen, how is that changing oxygen partial pressure related to the equilibrium here in this metal oxygen system. All right, so I'm stopping the recordings, and if there are some questions we can take